Today we're going to be talking about function transformations. Okay, we have two objectives. First, we're going to describe and graph transformations of functions, and then we're going to talk about the range of all the functions. We're going to look at three different functions today. So, the first thing we're going to look at is that every function in math shares the following transformation properties. F of x, so this line right there is transformed into this whole thing. Okay, now if you're looking at that and you're like, what the heck? Remember, let's think back on absolute value functions. So if you're looking at your paper, look up at the screen really quick. Absolute value functions, remember how we had a absolute value x minus h plus k? Didn't we have that for absolute value functions? Okay, and then what about we just briefly, so if you weren't here on Friday of the week before break, that last Friday before break, we talked very briefly, and it's okay if you don't know what I'm talking about, but very briefly about quadratics. So let's look here. This is what a quadratic look like. Now look how similar that looks, and look how similar both of these look to this function, right? Now, the top function is absolute value, and the one beneath it, this one, is a quadratic, right? But they both share that same transformation property. Okay, so I'm going to erase this. So if you wanted to write this down, that's fine. But that's just to kind of give you an example that, hey, look, we've actually looked at these before. So that should look familiar. That form should look somewhat familiar. Okay, so let's talk about A, H, and K. A. We've talked about this. So in all function transformations, in all functions that share this form right here, the A, H, and K are doing the same thing. Isn't that great? Because we're going to be working on this all year long. Not the same functions, of course, but we're going to be working on different functions. Okay, so the first function we're going to work on is quadratics, but it takes on the same exact transformation properties as absolute value function, the one we just did. So A, okay, let's talk about A. A makes the graph either more narrow or more wide, depending on what A is. Okay, so let's see, look at what makes the A more skinnier, so more narrow. So if the absolute value of A, which means if you're just going to take this number and you're going to take the absolute value of it, okay? So if A is greater than 1, we're going to have a vertical stretch. Now, a stretch actually means it's skinnier than the parent graph. So it's actually going to be like, it could be like that skinny even, okay? So it could be a super skinny graph. But the greater the number, the skinnier it is. So if A is greater than 1, we have a vertical stretch. Stretch means the graph is skinnier. If A, the absolute value of A, is less than 1, so if it's like a fraction, then it's a vertical compression. Okay, if it's a fraction that's less than 1, we have a compression. Compression means that the graph is going to be wider than the parent graph. So it could look something like that, okay? All right, and if A equals 1, if the absolute value of A equals 1, we have no vertical stretch or vertical compression. So the only thing we need to worry about, the only thing we need to focus on is if A is anything different than 1. Because if it's less than or greater than 1, we're either going to stretch or we're going to compress our parent function graph. Remember, a parent function is the simplest type of function we can have. Okay, so for the absolute value graph, remember the parent function looked like this. Right? We can't get any smaller than that. But we can put an A in front of that, and we can subtract something on the inside, and we could put a K on the outside, just like up here. Just like that transformation, we could transform that. But we can't get any smaller than this for an absolute value graph. Okay, that's all the parent function means. All right. A has two different things. So it makes the graph either more narrow or more wide. A also can flip the graph of a function. What the heck does that mean? Well, remember with absolute value functions, it always pointed up. It was a V, right? But if we had a negative A, so this would be a positive A, so maybe a 1, a 2, a 3, a 4, anything. If we have a negative number, it's going to look like this. It's just flipped. So if we have a negative A, so a negative 5, a negative 1/2, a negative any number, if we have a negative, it's going to flip and it's going to go upside down. Okay, so A can make the graph more narrow, more wide, and it can also flip the graph. So if A is negative, then there's an x-axis reflection. That's a fancy term for you flip the graph upside down. Okay? Remember, these are the same no matter what function you're given. H. So H shifts the graph left and right. We talked about that, right? So remember, if x minus H, then the graph shifts right. But if it's x plus H, the graph shifts left. Okay? And if it's x plus 0, and notice down here I also wrote or x. So if it's just an x or x plus 0, you won't see plus 0. So if you just see an x by itself and there's no minus or plus H, it's not shifting left or right. Okay? Now, K. Let's talk about K. K shifts the graph up and down. If it's a positive K, the graph shifts up. If it's a negative K, the graph shifts down. And what do you think if there's no K or if it's plus 0? It doesn't move up or down, right? So that's the basis of the transformation properties. You guys, this is so important. Please understand A, H, and K. Okay, all right, so A, there's two different things. Vertical stretch, vertical compression. If it's either greater than 1 or less than 1. Okay? If A is negative, it flips the graph upside down every single time. It just flips it over the x-axis. Okay, so it's going to flip it in the opposite direction. H shifts the graph left and right. K shifts the graph up and down. That's it. Those are the main things you need to focus on. Let's put this into practice. Okay, so let's look at a quadratic function. So parent math function. Remember a quadratic function? Y equals x squared is the parent function. What is a parent function? Again, a parent function is the simplest function you could possibly have. So y equals x squared, nothing can get smaller than that for a quadratic, right? We could add to that, but we can't take away anything. That's the simplest function we could possibly have as a quadratic. Okay, so this is what it looks like as a graph. Now, it's not a V, it's a U. I tried to draw that as best as I possibly could. It's always shaped like this, okay? Now, this, remember when it's a sharp V, that's an absolute value function, so be careful. On your mid-semester final, so on your first final that we're going to have in this class, you will have quadratics and you will also have absolute value functions. And if I'm asking you to graph them, I want you to make sure you know the sharp V is absolute value. This U shape, as much as you can possibly do a U in this case, that is your quadratic, okay? Okay, so that center point is called the vertex, right? The vertex is 0, 0. Now, on your absolute value function graph, vertex was right in the center as well. Remember, if this was an absolute value graph, this right here, that was your vertex, right? So in the same way, on this quadratic, your vertex is that either your vertex is your lowest point or your highest point. On this graph, our vertex is our lowest value. Okay, our range, remember range is always your y values. What is you start with the smallest. What's your smallest y? Well, this line is y, right? Is there anything underneath here? No, the graph doesn't even go there, right? It's only above that. So what's your smallest y value? Your smallest y value is 0, isn't it? So 0, remember we do brackets to include that 0. Okay, so 0, and then it goes until when? Well, does it ever stop? You see arrows that are going up, right? So it doesn't stop. So it goes from 0 to infinity. Okay, that is your range. Infinity and negative infinity always get parentheses, never brackets. All right, everything's coming together. It's all coming together. Okay, describe the transformations from the parent functions. All right, so this is, remember our parent function looks like what? It looks like y equals x squared, right? So what's happening from our simplest parent function, from y equals x squared, what's happening to this function? Well, a lot, right? So we need to pick it apart piece by piece. So let's start first with a. Now remember, look what I'm doing here. I'm doing absolute value of a. Why is that important? Because remember, if you turn back to the last page, if you look back at your notes that we just did, in fact, Let me go back, okay? So I'm going to go back really quick. What does it say about A? Let's look at A. It says if the absolute value of A is greater than 1, we have a vertical stretch. If the absolute value of A is less than 1, we have a vertical compression, okay? So let's see what this is talking about here. So the absolute value of A is greater than 1, isn't it? So vertical stretch. Isn't 2 greater than 1, right? Now, it's important that you take the absolute value of it, because that negative doesn't matter with the stretch or compress. So we're taking this whole A term, that -2, and we're taking the absolute value of it. Pretty much, that just means we're making that -2 positive. Then we're saying, is 2 greater than 1 or is it less than 1? It's greater than 1, so vertical stretch, okay? Since A is negative, this is when the negative comes in play. If it's negative, remember it flips. So we have an x-axis reflection. That just means it flips. The graph flips. So instead of looking like this, it's going to look like this because it's negative. Okay? So our A tells us 2 pieces of information. If it's a negative, it reflects over the x-axis. It's opening upside down. If it's greater than 1, I was looking at the 2, or less than 1, then it either stretches or compresses. We're done with the A. Now we're going to look at this piece. Okay? That x plus 2. Does x plus 2 tell you to go to the left 2 or to the right 2? So look back at your notes. That tells you left 2. Now we're going to look at this piece, that -2 at the very end. Does that -2 tell you to go down 2 or up 2? That -2 tells you, look back at your notes, to go down 2. That's it. And now we're done, right? So now we're going to graph it. Let's try graphing it. So the first step that we're going to do, the first thing we do when we graph is don't worry about the A. We can't worry about the A yet. We have to go left 2 and down 2. Where am I getting left 2 and down 2? Right here. We have to do those pieces first. Whatever is here, so look up at your screen. Whatever is here and whatever is here, we do that piece first. It tells us that x plus 2 tells us to go left 2, and that -2 at the end tells us to go down 2. So I'm going to do that first before anything else. I'm going to plot that point. Now I'm done plotting the point. Now I'm going to look at the A. Okay? I have to figure out, is it going to be upside down or is it going to be right side up? Well, that negative tells me I have an x-axis reflection, which tells me to point downwards, right? It's going to point like this instead of pointing up. Cool. Now, what about the vertical stretch? Don't worry about this too much right now, but we know it has to be pointing down. And stretch is going to make it wider or is it going to make it skinnier? It's going to make it skinnier. So I'm going to try my best right now to draw. See how it looks a little skinnier than up here, than that parent function? So that's all I'm asking you to do for right now. Okay? All I want to see is you're going left 2 and down 2 first. You know it's opening upside down, and you know it's skinnier because it's a vertical stretch. Got it? So those are the 4 pieces I just did. All right, let's try another one. What's going on? Oh my gosh. Okay, range. Yes, I'm sorry. I wasn't looking at the bottom. Okay, yes, range is negative infinity. So remember, we have to take the smallest y value. What is the smallest y value? Negative infinity, right? It doesn't, all of my information is down here. It's going to go on forever in that direction, to the negative infinity direction. So negative infinity is my smallest point. What's my greatest y? My greatest y is right here. Doesn't get any higher than this point, right? Well, that point is -2. So my range goes from negative infinity to -2. The negative infinity always gets a parenthesis. The -2 gets a bracket because there's no open circle. Now there's nothing up here, so there can't be any range up there. There's no y values up there, right? Okay, cool. Now we can move on. Describe the transformations from the parent function. So let's try again. We start with our parent function, which is y equals x squared. What's happening from y equals x squared to y equals 3 times x plus 1 squared plus 4. Okay, so let's take a look. I already labeled them A, H, and K. So we're going to look at first, since the absolute value of A is absolute value of 3, which is 3. There's no negative this time, right? We don't see a negative in front of that A. That means this is what your graph is going to look like, right? It's not going to be opening upside down. It's going to be opening right side up. That's really important to remember. Okay. So since it's 3, we're going to have a vertical stretch or a vertical compression. Vertical stretch, okay? Now we're going to look at the H piece. So we're going to say, okay, cool, I'm done with my A. Now what about, is it moving left or right? The X plus 1 means it's going to be moving left 1 unit. Now the plus 4 at the end, it's moving up or down? It's moving up 4, okay? So see how I pulled that apart? I want you to do the exact same things. So now let's graph it. So what do we graph first? Well, we have to graph left 1, up 4. These last two pieces you have to graph first. So look up at the screen. See how it's X plus 1 and then that plus 4 at the end? Graph that first. Remember that X plus 1 tells you to go left 1. That positive 4 tells you to go up 4. Do that first. Now I figure out, is it going to be opening up or is it going to be opening down? Well, it was a positive 3, so it's going to be opening up, right? And vertical stretch means it's going to be wider or it's going to be skinnier than the parent function. It's going to be skinnier, so I'm trying to draw it skinnier. Okay. And look how much skinnier that looks compared to this, right? It looks a lot skinnier than the parent function. So it's a good thing. Now let's talk about the range. Okay. Now what's my smallest, I guess it says right there, what's my smallest y value? Well, nothing is below here for the y, right? So my smallest y is at 4. Put brackets because I include 4. And it goes all the way up to, does it have a stopping point? No, it doesn't have a stopping point. So it's infinity, and you put a parenthesis around infinity always. Cool. Okay, this next one I want you to try. Describe the transformations from the parent function. I need to see this. Either right now, you can raise your hand when you're finished, or you can show me right after your notes, but I need to see this before we get on to the homework, okay? I'm going to be coming around and checking. So I want you to try this just to make sure I know that you're on the right track. If you have any questions, ask me, okay? I want you to describe the transformations exactly like we did before. Tell me what's going on here. Then I want you to graph it, and then I'm going to come check it, and then do the range. Let me write that. And find the range. Okay, so do that. And then show me. Oh, look at me. I already thought about that. Okay, so cubic function. Now, we're going to talk about 2 more functions. One of them is a cubic function. So cubic functions, okay, and then we're going to talk about square root. And these functions we're going to be doing also, but not right now. We're just going to be talking about the transformations. I want you guys to see, remember how important I said that this was. I want you to see what each parent function looks like. Remember the parent function for a quadratic looks like this. Remember the parent function for an absolute value looks like this. It's a V, right? What about the parent function of a cubic? Well, it looks like this, okay? Now, remember we're talking about range in this lesson too. So range here is always negative infinity to infinity. When you have a cubic function, 100% of the time, the range is a negative infinity to infinity, okay? So that's cool. That makes it easy. So let's take a look at an example. Describe the transformations from the parent function. Remember, we start with the parent function. What's my parent function for a cubic? X cubed. So x cubed. Well, look how similar this looks, you guys. Can we label A, H, and K? Do you guys see what A, H, and K is? Now, what's the only difference between this and my quadratic function? The only difference is this 3. That 3, instead of a 2, it's a 3. But we do everything else the same. Isn't that awesome? It's getting a little easier, you guys. Hopefully, you at least see the pattern. You're like, okay, maybe I can do this. So, look, absolute value of A. Its absolute value of A is 5. that means it's 5. What does that mean when you have a positive 5? Vertical stretch or vertical compression? It's a vertical stretch, right? Same rules. Since it's x minus 4, are we moving left 4 or moving right 4? Right 4, okay? Plus 6, are we moving up 6 or are we moving down 6? We're moving up 6. So it's exactly the same. Now, what's our range always? Look over here. For cubic, the range is always what? Negative infinity to infinity. How easy is that? We already know, right? Don't even have to question that. Now, I'm not going to have you graph these right now, but I just want to show you how awesome this is, that it all goes together. Okay, let's try another one for cubic, and then we're going to do one for square root, and we will be done. Okay, so if I said describe the transformations from the parent function, if I said my parent function was x cubed, and all this crazy stuff happens to the x cubed, let's figure out what's going on. Can we label a, h, and k? Oh, wait a minute. There's no h, is there? So be careful here. See how there's an x here, and there's nothing inside of the parentheses. That means there's no h. We have an a, because we have something on the outside here of the parentheses. We have a k, but we do not have an h. Do you see the difference compared to like this one up here? Right? So compared to this one, do you guys see the difference here? Why we don't have an h? I want you to take a very good look at that. There's no h, right? Okay, cool. Let's look at our a then. So we take an absolute value of a. The absolute value of a is the absolute value of negative 1/2, I'm sorry. The absolute value of any negative number is a positive. So a, the absolute value of a is 1/2. That means we're going to stretch or compress. Since it's less than 1, we're going to compress. It's a vertical compression because 1/2 is less than 1. Take a look at your notes from the very beginning if you're confused. Okay? Now, since a is negative, right? Look at your screen really quick. See right here? See how it's in negative 1/2, right? So that means it's going to have an x-axis reflection. Okay? Since there's no h, does it move left or right at all? No. We're not moving left or right. It's staying right there in the middle on the 0. Okay? We're not moving left or right because there's no h. Now, since k is negative 1, we're going down 1. Cool. Okay, hopefully you guys understand this. Now, what's the range? Always for cubics. Negative infinity to infinity. All right. One more example. Okay, so we're going to go on to our square root function. Now, this is what the simplest form of a square root function looks like. Y equals square root of x. Can we get any smaller than that for a square root? No, not at all. That's the smallest we can get. Now, what does a square root function look like? Well, it looks like this. So notice that the square root function starts at 0, 0, and it only goes in this direction. Let's think about this for just a second. If I put a negative inside of my square root, can I do that? No. So for example, because why is the graph not over here at all? For this reason. If I said square root of negative 4, is that a real number? No. So I can't plot anything on this side. I also can't plot anything down here. A square root is not, you cannot take a square root of a negative. It always has to be positive. That's why my square root function is in the positive x and the positive y. Isn't this quadrant, remember this is quadrant 1, right? Isn't this quadrant positive x, positive y right here? So that's why my square root function goes in positive x, positive y. All right, now, like I said, last one. Let's just, and the range. Okay, the range is from 0 to infinity on my parent function. Why? Because this is my y line down here, right? Does it get any lower? Is there anything down here? Nope, it starts at 0 and it goes on forever in this direction. It's just going to keep going on. It's going to get bigger and bigger and bigger. It's going to get bigger slowly, but it's going to go on forever, okay? Forever in that direction. Cool, let's talk about an example. So it says describe the transformations from the parent function. My parent function, what is it? Y equals square root of x. Let's transform this. So let's say I was giving you y equals 3 times the square root of x plus 2. What's different from here? Look at your screen. What's different from here to here? Well, a couple things. Let's identify a and h. So here's a and h. Is there a k? No. Now this is what a k would look like. Everybody look at your screen. If I had plus 2, all of a sudden I have a k, don't I? Then I would say, okay, cool, this is my k. But do I have a k in this case? No, there's nothing on the outside, right? So there's nothing being added or subtracted on the outside, so that we only have a and h. Let's talk about it. Since the absolute value of a is 3, then are we going to compress or are we going to stretch? It's going to be a vertical stretch, okay? Anytime it's greater than 1, it's a vertical stretch. Cool. Now let's talk about since x plus 2, since it's x plus 2 on the inside here, since it's x plus 2, we're going to go left 2, we're going to go right 2. We're going to go left 2. Okay, do I have a k? No. So since it's plus 0, since there's no k, we're not going to go up or down, right? So it's just plus 0. If I said plus 0, does that change anything over here? No, if I added 0 on the outside, that doesn't change anything. Okay, so there's nothing there because you're just adding nothing. If you add nothing, it doesn't change it, right? So there's no k. All right, now let's graph this just for fun. So I know what you're thinking. I know you're thinking, Miss Earl, that's not fun, but I want to show you how this looks. Okay, so let's look at this. Now, where do I start when I graph? I start here. Didn't I tell you you always start here and then the k, right? But there's no k. So I always start at h and k, and I'm going to graph that point first. What's my h? My h is 2. So remember I said right here? Oops, I just crossed it out. It wasn't what I meant to do. Left 2, right? So we're going to go left 2. Are we going to go up or down? No, it says no up or down. So all I'm doing is making left 2 and I'm making a point. Okay. Now what do I do from there? Well, I have to make it look like this, right? That's my parent function. You guys, this is just practice. So if you understand where I put that point, you're good. We're not doing this. We're not doing square roots right now, but I want you to just see how this works, okay? Then I would graph it that way, right? Now my stretch, did I stretch it out? Yeah, I stretched it. It looks a little taller than this guy over here, doesn't it? So I stretched it out. Perfect. I know I'm just going to go left 2. What's my range? What's my smallest y value? Well, I'm looking at y. I'm looking here. Is there anything over here, under here, for y? No. What's my smallest y value? My smallest y value, isn't it here? Isn't my smallest y 0? And then what's my greatest y? Infinity. So that's my range. Okay? Now, like I said, we're not working on square root right now. And we're not working on cubic functions right now. We're just working on quadratics. So, but I wanted to show you, isn't this awesome? I feel like you guys should be excited that they have the same rules. It excites me because it's going to be so easy to apply. And I wanted to show you, oh my gosh, look how awesome this is. It's going to be easy to apply. Now, I want you to show me that one problem I wanted you to work on for quadratics. And I just want, all we're touching base on right now is transformations and range. Do you understand how to look at a function, whether it be square root, cubic, or quadratic, or absolute value, and take a, h, and k, take those pieces and talk about it? That's what your goal is here. And then to understand the range. So we're going to do MyOpenMath after this, but just make sure you do that example and show it to me.